Hello everyone, in this video we will learn about molecular compounds and covalent bonds. In the previous video we mentioned that nonmetals and metals can come together, transfer electrons, and constitute ionic compounds, also known as salts. But when nonmetals would like to make bonds together, the transfer of electrons is no longer an option. They'll have to share their electrons. Suppose you have a pen and you need a second pen. Your friend has a pen and he needs a second pen. What you can do is you can share your pens with each other. That way you have two pens and he has two pens. And that's the case with the H2O molecule. Oxygen is a group 6 element. That means oxygen would have 6 electrons in its valence layer. Hydrogen is in a group 1 element, which means it only has 1 electron in its valence layer. What oxygen does to form two covalent bonds and satisfy its octet desires is it shares its single electrons with one hydrogen each, and that way it forms two covalent bonds and makes the H2O molecule. Another example is the CH4, the methane molecule. Carbon is in group 4. Carbon has 4 electrons, hydrogen has 1 electron. So carbon shares its electrons with 4 hydrogens, constitutes 4 covalent bonds and methane molecule. Now, what's important about this is you just learned that every 2 electrons shared between non-metal atoms constitutes a single covalent bond. Let's explore a case where there's a double bond involved, such as formaldehyde. Carbon group 4, oxygen group 6. That means they have 4 electrons and 6 electrons in their valence layer respectively. And we have hydrogens with each 1 electron in this valence layer. So what carbon and oxygen can do to ameliorate oxygen's desire for octetness is to share 2 electrons with each other, constituting a double bond. After all, if 2 electrons shared constitutes a single covalent bond, 4 electrons shared would mean a double bond. And then the remaining electrons on carbon could be shared with hydrogen, forming the H2CO or the formaldehyde-Lewis structure. What is important about this slide is that not only you learn the basis behind covalent bond formation, which is to fulfill the octet desire, or at least come close to fulfilling it, but you also learn how to draw the Lewis structure of molecular compounds. There are electrons that are shared, they're bonding electrons, and they're turned into bonds at the end of the bonding process. But there is also non-bonding electrons, lone pairs, that are there before any bonds are formed, and they're there after all the bonds are formed, like the ones with formaldehyde. So if you look at the oxygen lone pairs on the oxygen, they're there before all the bonds are formed, and they're there after the bonds are formed. Those are known as lone pairs or non-bonding lone pairs. We can practice some more by drawing the Lewis structure of methanol. The good thing about this question is that we already have an idea how to furnish the elements around each other. As you can see, carbon is in form of a CH3. Carbon is surrounded with 3 hydrogens, and then next to it there's an oxygen, and next to that oxygen there is a terminal hydrogen. So we can just, we can follow that format. Carbon is in group 4. We furnish it with 4 single electrons. If there was a 5th electron, one of these electrons would be a lone pair, right? So we start every Lewis structure by assigning single electrons, and then after that first round is complete, we start doubling it up until there's 8 electrons. But since carbon is 4 electrons, there's only 4 singles around it. All right. Then there's hydrogens. Each hydrogen would have 1 electron. There's oxygen next to carbon, which is group 6. So 1, 2, 3, 4, 5, 6. That will constitute 2 single electrons and 2 lone pairs. And then the terminal hydrogen, just like any other hydrogen, has 1 element. So logically, how would we splice this up? How would we share these electrons? Well, carbon could share 3 of its electrons, actually all of its electrons, with 1 electron from the surrounding elements. What remains is an oxygen and a hydrogen, so they can share their electrons and constitute the 5th covalent bond, which if we were to convert these bonds, these shared electrons into bonds, will look like this. Pay attention that the lone pairs on oxygen are still there after all the bonds are formed. If you want to test yourself some more, you can do the following question. Naming molecular compounds is simple but different than naming ionic compounds. In ionic compound, you don't have to worry about how much of any component is there. When I say calcium carbonate, you already know there is 1 calcium molecule, calcium ion, and 1 carbonate ion. Where I say it's magnesium chloride, you already know there is 1 magnesium and 2 chlorides, because the charges belie the amount of the moles of every, or the ratio of every component. But in molecular compounds, you have to specify of how many of every element you see, and what's the identity of the element. For example, carbon monoxide. You see one carbon, you see one oxide. Carbon monoxide. Carbon dioxide. You see one carbon and two oxygens. Carbon dioxide. Same thing with nitrogen dioxide. One nitrogen, two oxide. But two nitrogens and five oxygens would be dinitrogen pentaoxide. How do you know a molecule? How do you tell a molecular compound from an ionic compound? Very simple. If you don't see any ions that are constituting that compound, then and you only see non-metallic elements, then that most likely is a molecular compound and follows the molecular compound naming rules versus the ionic compound nomenclature rules. We can test ourselves by naming the following compounds. Again, when you're naming a compound, you have to ask yourself, is this an ionic compound or a molecular compound? CO, two elements sharing electrons, molecular, carbon monoxide. Same thing, carbon dioxide. Same thing with sulfur dioxide. Same thing with hydrogen, dihydrogen oxide, or simply water. Dihydrogen peroxide, dihydrogen dioxide, or hydrogen peroxide is its common name. Nitrogen monoxide, nitrogen dioxide, carbon tetrahydrate, but nobody says that, everybody says methane. Diphosphorus pentaoxide. Right now we have two phosphorus, so diphosphorus pentaoxide, and then vanadium and sulfide. Vanadium is a metal, so you can say divanadium trisulfide, but that wouldn't do justice to it because vanadium is a metal and sulfur is a non-metal. So you'll have to follow the ionic compound nomenclature rule, which says vanadium, which is a transition metal. So you have to specify that it has a charge of 3. How do I know it's a charge of 3? Well, look at the subscript for sulfur. Sulfur's subscript was vanadium's charge. So vanadium 3, sulfide. You don't have to specify the charge for sulfide because sulfide is group 6 nonmetal. It only can have S2-. This concludes our presentation. Thank you very much for viewing.